Great. So our next speaker is Mboyo Esole from Northeastern, and he'll be telling us about the birational geometry of elliptic fibrations. So thank you very much.
Hi, everybody. It's a pleasure to talk here. I recognize many friends, especially talking after Lara, who did a lot of great introduction on the material that we cover. So we have some intersection, but thanks to her, I'll be able to go straight to the point. So I'll be talking about aspect of elliptic fibration and especially the relationship with representation theory. So this is in the context of geometric engineering. So as Lara explained and many others explained before, the idea of geometric engineering is to try to use geometry to represent reality, at least reality as seen in string theory. And one way why this is possible is because in string theory, you have compactification, and this compactification bring a relationship between a property of the extra dimension and property of the physics you are trying to describe. So in my case, the tool that I use mostly is algebraic geometry. So now algebraic geometry is a very old topic, depending on how you define it. You can see sign of using polynomial already 1800 BC. You have these tablets that collected numbers that I call a Pythagorean triplet in Babylon, and you can think of it as an example of using polynomial. So when we think of string theory, obviously we have this idea of strings that propagate in space-time, and it's the geometry of the extra dimension of space-time that will be the focus here. So as you do string geometry, your description is not always complete, in the sense that there are some aspects of string theory that has nothing to do with the geometry. So you try to describe as much as you can. And surprisingly, you can really say a lot just using the geometry. So here we can dive. So this slide really is just me saying hello to my hometown of Kinshasa. So you see the Congo River here and fishermen on the river and the sunset. Beautiful place. So let's go back time ago and look back what happened just before the beginning of the 20th century. So in this timeline, I put some points that represent important results in physics and in mathematics. So in 1892, you had Lorentz who introduced the Lorentz transformation. That is basically what we use to describe space-time without gravity. Then in 1894, Cartan had the classification of simple Lie algebra. And just 2 years later, Frobenius wrote the paper that people consider to be the birth of representation theory. The year after, Thomson discovered the electron, which was the first fundamental particles to be discovered. And then 3 years later, Planck introduced the notion of a quanta. So within like a 10 years period, we completely changed the way we think about things. And the basic tools that will describe the physics of the 20th century, gauge theories, many aspects of condensed matter, and all of experimental particle physics were kind of like set up in this time. So now I'm going to talk about this in the context of elliptic fibration. And thanks to Lara, I don't really have to tell you what is an elliptic fibration. But what I will need you to just remember is that elliptic fibration was studied by Kodaira. So that was around 1962, 1964. And Kodaira is a Japanese mathematician, one of the best geometer. So he was this type of geometer that will use tools from geometry, analysis, algebraic geometry, and will be just able to surf from one to the other to basically study the object that is in front of him. Nowadays, people specialize a little bit more. So when you read Codera flavor of paper, they come with a certain flavor of a real master playing with his tools. And so Codera wanted to classify algebraic surfaces. And in the context of his classification, he had to single out a very special case, the case of elliptic surfaces. So elliptic surfaces are surfaces that locally look like a curve, a complex curve, on which you have an elliptic fibration. And in this classification, as you think of fibration, they are really characterized by their singular fibers, because otherwise it's a little bit boring. And the singular fibers have this particularity that just if you think of a field, a subject like elliptic fibration, you might think there might be 1,000 of different possible type of singular fiber. But what Codera show in the case of elliptic surfaces, the number is actually relatively small, depending on how you count it. You can go from 9 to 10. Tate has produced an algorithm that rely on the Weierstrass model that Laura was talking about to basically pinpoint what type of singular fiber you can have. So here, this is one of my rare slides with equations. So I write the generic equation of Weierstrass model, and it's basically a cubic curve that has a specific form. One way to think about this, so some people really don't like to see two equations with so many terms, but this equation is completely characterized by the geometry in the sense that once you pick up a line bundle on your elliptic fibration, so you make a choice of a section, the Weierstrass model will follow from just using Riemann-Roch theorem. And if you don't work in characteristic 2 or 3, you can reduce it to a shorter Weierstrass model, which is basically the type that Weierstrass considered back in the days. And there is an object called the discriminant of the Weierstrass model that tells you what, where are the locus of singular fibers. And if you study the multiplicity of all these coefficients along a divisor, you then can use this information in Tate algorithm to figure out what type of fiber you have. So it's a little bit technical, but it's the nice type of technical because it gives you an algorithm that turn questions into, that give answers to questions. So then just to illustrate a little bit the structure of the singular fibers. So singular fibers are always of the type extending Dynkin diagram. So if your Dynkin diagram is of the type ADE, there is no complication. There is only one way to extend them. But you also have those that are twisted. And here you have different options. And elliptic fibration use the left option. And the twisting can come using a monodromy. So meaning two nodes should be considered the same node. If you go along the loop, they get exchanged by some symmetry. So this happens very simply when you start considering fibration over something bigger than a curve. So once you start looking at elliptic threefold, you can produce this type of Dynkin diagram of type BCFG. So, okay, so now what I want to do is to ask the following question. So I have an elliptic fibration. It has this collection of singular fibers. So using the singular fibers, I can decide what is the Lie algebra of the gauge theory that describe associated with this elliptic fibration. But then, as you know, in physics, we're not just interested in the Lie algebra of our Lie group. We're also interested in other things like what is the global structure of the liquid, for example, or maybe something even more profound, what are actually the matter representation associated with that geometry. The matter representation are essential, especially if you work, let's say, in 6D, where you have to cancel anomalies, because they have to balance themselves in a way that they satisfy the anomaly condition. So Katz and Vafa, they came up with a very intuitive way to answer that question, especially if you compare with the alternative. So you basically say, okay, I have this singular fiber that specializes in higher codimension to another type of fiber. And so you take your initial fiber, you look at the specialization. So this gives you two types of different Lie algebra, and you ask yourself how they can be embedded into each other. So one will be inside the other. And then you take the complement representation. And this complement representation was already introduced by Dynkin in his work on just understanding embedding of Lie algebra, and he called it the characteristic representation. So from the point of view of Katz and Vafa, they did their work during the second string revolution. They were not aware of Dynkin work. They were interested mostly in the reduced form of this characteristic representation. So first of all, just if you look at it, the adjoint representation is always a real representation. So you have two adjoint plus a complement. So the characteristic representation will also be a real representation. And because of that, it always takes the following form. You will have a real part. The quaternionic part will come with a copy of itself. Then any complex part will come with complex conjugation. So this structure is just imposed because of the fact that we're talking about a decomposition of a real representation by another representation. But however, you immediately see that it also satisfies condition that you will naturally impose in physics when you think of your representation. They will also be real and satisfy this restriction. But here it's purely the result of just the mathematical context we are in. So now, let's try to see if the Katz-Vafa algorithm really works. So if I have a Lie algebra and I have a smaller Lie algebra inside itself, can I really do a decomposition using the adjoints that uniquely tells me what the matter representation would be? And actually, if you're a mathematician working in physics, you know that the answer is probably going to be no. And that's the case here as well. So it does not actually work for the following reason. The same subalgebra G so the same Lie algebra G that is inside M could actually have copies that are explicitly isomorphic to itself, but are embedded in a completely different weight inside M in such a way that if you do the decomposition, you end up with different branching rules. So you end up with different representation. So here, what it means is that when we talk about Katz-Vafa, we just have to be careful to define the problem with a little bit more data. And here, the additional data that we need is to introduce the notion of embedding. Instead of focusing on the isomorphic class of M and G, we should really think, how is G embedded inside M? And once you start focusing on the notion of embedding, you can then introduce the notion of equivalent subalgebras that are such that they can be linear move from one to the other. They give you the same decomposition of the adjoint, and they give you the same matter representation. So the question now is, okay, so we have this notion of the Katz-Vafa decomposition using the notion of characteristic representation that is naturally described by the work of Dynkin as well. But how do we actually decide when we have many possibilities, which one is the one selected by physics? So to make a decision, we need maybe to try to think what are the type of ingredients that can give us additional information on the embedding. The embedding is a bit abstract, so maybe we can use some number associated with an embedding. And one way to do it is to use the killing form. So as you know, the killing form was introduced by Cartan, and the Cartan subalgebra was introduced by Killing. So sometimes you do have some Z2 symmetry in way mathematical objects are named. So here, the killing form will be obtained if you work, for example, with matrices by taking the trace when you consider the adjoint of each element. And we normalize it in such a way that the longest root will always have length 2. So this renormalization here is very critical because of the following reason. Suppose you have a representation of a Lie algebra into a linear space. You can then introduce the notion of an embedding of that Lie algebra. And when you do the embedding, you can also move the bilinear form from one space to the other space. And when you do that, because of the normalization, just taking the trace of fx, fy will not necessarily produce you a bilinear form for which the highest root will have length 2. So you have to renormalize it. And this renormalization factor, which here I call LF, characterize in a certain way your embedding. And so this number is called the Dynkin index of the representation. And it is a beautiful fact that the Dynkin index is always a positive integer number. To prove that it's actually a positive integer number was quite a lot of work for Dynkin. He basically did it by computing all the possible cases. And then a few years later, a more beautiful proof appeared that was related to the topology of the Lie groups. And this aspect will come back at the end of the talk. So when your representation decomposes into many other representations, the Dynkin index can be obtained by using a weighted sum, where the weight factors are basically related to the multiplicity of each irreducible representation. So this formula also tells you the beautiful fact that if you actually know the Dynkin index of a collection of representation that generate every other representation, it's enough to compute all of them and to study property of all of them. And that's exactly what Dynkin did. So he computed the Dynkin index of all the fundamental representation of all the simple Lie algebra. So using that, you can then compute the same for any type of representation of any Lie algebra. And remember, this is a property of the Lie algebra, not a property of the Lie group. So that's also important. And as you can see, these numbers sometimes can be pretty big. They are often even numbers when you look at G2, F4, E6, E7, and E8. But for the series A, B, and C, other things can also happen. So when you have a more general embedding, you can also use the same trick to represent, to define the Dynkin index of the embedding itself. So now we have this situation in which we know that when we have two Lie algebra, we should not just focus on the isomorphism class. We have to think of the embedding, and a little summary of the embedding can be given by the Dynkin index. And it would be nice if the Dynkin index could actually somehow be the parameter that give us an information on the type of representation we expect to see in string theory, at least in the generic cases. So here, we're going to make an interesting observation. So this table, the first column of this table on the left represent the typical embedding used in the Katz-Vafa paper. So you basically have embedding when you embed into a Lie algebra that has a rank 1 higher than the one you started with. And in terms of Dynkin diagram, you can always think of it as if you were adding a node to your Dynkin diagram. Then here we compute the characteristic representation, and then we compute the Dynkin index. And if the Lie algebra that you embed in the parent Lie algebra has multiple components, we compute a Dynkin index for each one of them. And now if you look at the right column of this table, you notice that everything has Dynkin index 1. And so this observation was done only very recently in a paper in collaboration with my dear friend, Monica Kang, who is a postdoc now at Caltech. But it really came like as a surprise, because why will we just have Dynkin index 1? What is special about Dynkin index 1? Why not Dynkin index 2, 5, or 1,000? And so that's what I'm going to try to explain in the rest of the talk. First, let's make it clear that Dynkin index 1 is actually not always the case. So I'm going to consider the simplest embedding we can think of. Let's embed the Lie algebra A1 in the Lie algebra A2. And the decomposition here will depend on the Dynkin index. There are two possibilities. You have one embedding that has Dynkin index 1, and the matter representation will give you the fundamental representation of SU2. But if you have Dynkin index 2, you end up with the representation that is the 5. And you can see immediately that the one that you will naturally associate it with the brain is the fundamental representation. You're thinking of open string between two D brains, and you will have a doublet, and that's the one that has Dynkin index 1. So somehow, if we didn't know about D brains and open strings, but if we knew that we should select the one of Dynkin index 1, we're still going to get the right answer. So then we can think of it as maybe this is an interesting conjecture to have, and then to try to explain mathematically and physically. So the strategy here would be composed of essentially 3 parts. So number one, there are situations in which you don't really have a lot of diversity in the question. There is only one way to embed a certain Lie algebra into others. And so then you basically end up with what you have. Those cases, we call them singleton subalgebra. They are almost like prime number. They sit alone. They don't talk to anyone, and they are the only one of their kind. They are the only option. Then you can have a situation in which the same Lie algebra can be embedded in many different ways. However, each one of them, which is not linearly equivalent to the other, still gives you the same decomposition of the adjoint representation. So in that case, you can even ignore that they're different, because from the point of view of just getting the characteristic representation, they give you the same answer. So we call them adjoint singleton subalgebra. And so what happens in the case of the Katz-Vafa, for the classical cases that everybody studies, they are of the first or second kind. So basically cases where you do not have an option. So it means that even if you try to explain this by D brains or by apples and potatoes, it doesn't matter. You will end up with the correct answer, because there is only one possibility. Then you have the cases where you do have the same Lie algebra that is embedded in many different ways, but each way gives you a different representation. In those cases, we will use our conjecture that the correct choice should be the one of embedded Dynkin index 1. And to test it, we use the use database that we build over time by doing resolution of singularity of Weierstrass models. So the idea is that before we had this way, organic way to think about it, we were doing it by just showing our strong geometric muscles. So you give us a Weierstrass model, we identify the discriminant blockers, we identify all the different type of singularities that it has, and then we just start doing surgery on that geometry to smooth everything so that if there is no more singularities, everything is smooth, and then we can study what we get. So there are many ways you can resolve the singularity of a geometry. So we put some restriction on the way we use, and typically we will ask the resolution to be a crescent resolution. So what it means is that you preserve the canonical class. The canonical class is almost like a God-given class on a given algebraic variety. So preserving it is a big deal geometrically, but especially in physics, because as you heard in the talk of Lara, the type of geometry that people typically study are Calabi-Yau varieties, and they are characterized by having a trivial canonical class. So when you do a crescent resolution of a singular Calabi-Yau, you end up with a smooth Calabi-Yau. And the notion of resolution itself, I didn't explain it. So what it means is you replace a geometry, an algebraic variety by another, but you do it in such a way that you do not touch what is not broken. So all the parts where there are no singularity will be left untouched, and the part that have singularity will be replaced by something else. And that something else is typically what produce the singular fibers, because a Weierstrass model only have fibers that are just curves that are irreducible. And once you do resolution of singularity, you are adding cycles and so on, and you end up with the beautiful Dynkin diagram that we have seen before. And in higher codimension, they can collapse in objects that you can think of as Dynkin diagram, where you remove some nodes, when you glue some nodes together, and so on. So, so in this paper with Monica, we essentially went through the list of all the resolution that we have done over the years, and trust me, each one of them is almost like a, a spiritual experience because it takes a lot of work to do it. And we were able to find which representation was selected by the physics geometrically by basically looking at the structure of the singular fiber when they specialize in higher codimension. And then we were checking that everything were correct using anomaly constellation. And each case represent like hours and hours of work. But with this conjecture, we are able to do it so fast that it's almost annoying, because you think like, what the hell? Why is the world so unfair that you can spend so many years working hard, and then all of a sudden you realize that maybe you didn't have to do so much work. So, so now I'm going to try to explain why this Dynkin index 1 conjecture actually works so well. And the reason why it works so well is almost trivial if you are familiar with topology of Lie groups. So before I was always talking about Lie algebra. So here, because I'm going to introduce notion of topology, I actually need a Lie group. But for each Lie algebra, you can associate the Lie group that is simply connected so that you don't have to deal with multiple options. So these are the ones that I will consider here. And in the study of homology, just the structure of a Lie group, there are certain homology homotopy classes that play a special role. One of them is the H4 of the classifying space. So the classifying space is BG. and kind of control the type of connection you can put. It tells you a story about more than just the algebra, but the additional structure you can put on it. I wish I could actually just talk more about what it means, but we're not going to have time. Then there is the third cohomology group of the Lie group. And here I always work over Z with Z coefficient. And then you have the third homotopy group of G. And anyone who has studied the topology of Lie group recognize that these three groups are special because they are the first non-trivial one that you get when you work with a Lie group.
Sorry, you have just 10 minutes left.
Thank you. Okay, so here, now before we were talking about embedding of the algebra. So now let's assume that we are considering an embedding of Lie groups. And we know that there are a lot of information you can get from the Lie group, but we want to focus on these three specific objects. So the H4 of the classifying space, the third cohomology group, and the third homotopy group. And each time you have an embedding, you also have an induced embedding for the different group that we consider. And the direction of the arrow really is what you would expect for cohomology and homotopy. So in the case of cohomology, you reverse the arrow, and for homotopy, you keep the direction of the arrow. And then you can ask yourself the question, what happens in this embedding? Is this like a way to see the Dynkin index in a natural way? And the answer is actually yes. And it's yes for a very beautiful reason. Each one of these groups is actually a cyclic group. So meaning each one of these groups is characterized by the fact that it has a unique generator. So now think about just two groups that are defined by one generator. So you can think of them as the additional group Z with plus. And so it means that if you want to define an embedding between them, the only thing you have to say is, what do I map the unit of the first group as a multiple of the unit of the second group? So it means these embeddings are characterized by a unique integer number. And it happens that this unique integer number is exactly the Dynkin index. So that's the link between the Dynkin index and topology. And another way to think about it is you can compute the co-kernel of these embeddings, and they give you cyclic groups, and the cycle is the Dynkin index. Now, if you think in terms of gauge theory, you can define instantons, for example, that have certain couplings, and then you ask yourself, after an embedding, what happens to the kinetic term of your theory? And what happens to them is that the inverse of the square of the G of the group will basically be rescaled by the Dynkin index. So it means that if the Dynkin index is different from 1, you can start from an instanton that is of minimal charge, and then you replace it when you embed it in a larger group by an instanton that actually has a multiple charge, so can decompose into a smaller instanton. So when your Dynkin index is 1, you basically preserving the minimal charge of the theory. And that's what this conjecture ensure that you will do. So now I think I practiced well. This is my last slide. So now you hear and you understand the physical meaning of having embeddings of Dynkin index 1. So what they do for you is that they preserve a lot of information that you would like to preserve in the simplest case when you consider physical models. So here you will preserve the spectrum of your instantons. So you put in H inside So basically, when H reduces to G, you do preserve what is the minimal charge. So you're not going to get something that was supposed to be stable and all of a sudden start decomposing in different parts. You also preserve the classifying of the Chern-Simon terms. You preserve the classifying of the West-Zoom-in or return terms. And there is also a matrix that is, maybe this is a technical details, but you have an embedding matrix that will have orthonormal rows. I'm not saying an orthogonal matrix because it's not necessarily a square matrix. But if you just look at the row, they will have a scalar product that will give you the unit matrix. And then anytime you do a repetition, so you embed one into a bigger group and then into a bigger group, you do preserve the Dynkin index because the Dynkin index is multiplicative. So to summarize, what I have done here is I've shown you that for us geometers, people interested in string geometry, we spend a lot of time working with singular geometry that we basically cure of their singularities, respecting some fundamental condition to make sense of the physics. And there were a very painful way to do it. But then if you need a fast answer, you had the option to use the Katz-Waffa technique. However, the Katz-Waffa technique was not well defined. Once you define it well, you realize that sometimes you have more choices than you need. And the talk was to tell you that when you have more choices than you need, choose the one that has Dynkin index 1. And what it will do when somebody asks you, why will you do it? What does it mean for your physics? It basically the choice of simplicity. It will preserve a lot of the typical invariant you're interested in. And I would like to mention as well that there are physical interesting cases in which you have embeddings that are not of Dynkin index 1. And such cases are usually configurations that are very special in many ways. So for example, in F theory, you have what people call exotic matters, matters that are not what you would expect. You have an SU2 theory, but the matter does not give you the fundamental matter. So all those cases, when we check them, they are characterized by the fact that they don't have a Dynkin index, an embedding that is 1. So it would be interesting to study further what that means. And this is the end of my talk.
Great, thank you for a wonderful talk. Are there any questions? Laura has a hand up.
Sorry, I was just clapping.
Oh, okay, good.
Really nice talk, though.
Thank you.
And I have a sort of very naive question. So these examples where you have a Dynkin index that's not equal to 1, is that because there are no branchings with Dynkin index 1, or something in the geometry is telling you should pick the branching with Dynkin index not equal to 1?
So on the geometry side, what you just see is that you have singularities that are not generic. So so the configuration that don't have Dynkin index 1 are configuration that we actually don't understand very well. A lot of people think they should be included, and I think they should be scrutinized. So we need to understand like what actually is, if there is actually something wrong with them, because they're so different. Like if you think of it as a statistic, they will represent like 0.00 something of all the existing cases. And so it would be interesting to study them much more. So we knew they were special geometrically. Now we know that even if you look at the quantum structure, they seem to behave differently. And so it will be interesting to see if they really exist out there, or there are cases that really have some fundamental problem with the physics. But my intuition is that usually when something you show something in physics, it is relevant for one reason or another. It's just a matter to identify what it really means.
Interesting. Okay, thank you. Are there any other questions before we move on? Okay. Well, other questions, they can raise them offline. So let's thank Mboyo again.